Me llamo Vincent Jourdain. No hablo español, sí, hablo español muy mal, ¿ok? Pero no es importante. ¿Qué es importante? Es que tú sabes más después de este curso. So, hablar inglés o francés bien es no importante, es no importante. Si tienes queridas, eh, tú, tú, tú tienes querer. ¿Entiendes? ¿Entiendes? Ok. Ok, en inglés o en español y Fernando will translate or anyone. Okay, so we can close maybe the door. It's okay. Uh, hablo en inglés. Okay. So this course is about carbon nanostructures, and it will be mainly devoted to the structure of carbon nanostructures first, and the synthesis tomorrow. So I'm going to talk about that. So carbon nanostructures. You got this course about carbon nanostructures. Is it really an important course? Well, you can wonder. So these materials, carbon nanostructures, you have some examples of them here. This is a fullerene, this is a nanotube, this is graphene. Are they really important? So to give you some ideas about how important this subject may be, I show you a few slides as an introduction. So, fullerenes were first discovered in 1985. Nanotubes were discovered later in 1991, and graphene finally, much more recently, was isolated and started to be studied in 2004. What happened in the lab during this period? This is the first indication of the interest of scientists and of people in the lab for carbon nanostructures. So it's better. Yeah, you can hear me? Much better. Yeah. Okay. If I speak too fast, you tell me also. Then, here we got discovery of the fullerenes in 1995. Then discoveries of nanotubes, and here you got the number of publications per year for those three different subjects. What you can see is we start having a lot of fullerene publication in this blue curve here. So and it started to stagnate at about 1993, at about 1,800 publications per year. Then you got nanotubes. Nanotubes, it was slower, but finally it reached a much higher value now in the 2007, 2008 year. And then in green you got graphene. Graphenes, the studies really started in 2004, and since then it increases exponentially. So this gives you an idea about the interest about those materials in the lab. But is it really important for applications? Well, also, I may cite that there was 2 Nobel Prizes attributed for those those materials, one in chemistry and one in physics. What about application? So this is a graph about the number of patents. Okay, patents on carbon nanotubes and graphene and fullerenes as a function of time. This gives you an idea about the interest of companies, industrials for carbon nanotubes. Okay, patents is okay for everybody? Patents? Okay. So you've got these curves. These curves look really like the curve for publications, except that it's a bit, patents usually come a bit later than publications. And also you see that there are many patents on graphene, even though it's quite a new subject. So this is a first indication, the number of patents as a function of time. And here you see that in 2010, for instance, there was about 2,000 patents for nanotubes only. And for graphene, it's already like 400 patents in 1 year for including graphene as material. So it looks like companies are really interested in those materials. Other aspects is you can look at the numbers, the figures in terms of money. So nanotubes is now starting to boom as an industrial point of view. So you've got a high growth rate, you've got a market which is expected to be about $1 billion in 2011. And concerning graphene, you got an increase. It started to be much faster. And big companies and many countries start to investigate a lot in those materials. Okay. Why are they important? Why do companies and countries want to invest so much money in those special materials? Okay, there are first a fundamental interest. What I mean by fundamental is, can those materials bring novel or improved knowledge? Okay, just knowledge. The thing is, those structures are novel form of carbons. Carbon is a very important element in our world. It's the basis of life, the basis of organic life. Many of the compounds and material we use, like plastics, are based on carbon. So carbon is an extremely important element for our daily life. And here we have discovered new structures, new forms of carbon. Previously, what we knew as forms of carbon, we talk about allotropes also, like different forms of carbon are allotropes. Allotropes of carbon, already known, were graphite and another one. Could you tell me another form of carbon which was already known before? Graphite and girls? Diamond. Good answer. Okay, so except those two, we did not know about a structure which was just pure carbon. Here we got just pure carbon like graphite and diamond, but at different forms. So this is just interesting on a fundamental point of view. It tells us that we can make novel forms of carbon because of the special properties of this element. We are going to talk about that in detail after. Okay, so this is about carbon. The other important word is nano. Okay, what is important about nano is that the physical laws change when we go from the macroscopic scale to the nanoscopic scale. There is a modification of the properties. The properties then at this scale become extremely dependent on the size, okay, the nanometric size. And then at this scale you got something between atomic properties and macroscopic properties, and between let's say like one carbon atom and a crystal of graphite, then the properties are different between those two. And but there must be a continuum of properties. So when do the properties change? They start changing at the nanoscale. This is where the properties start to change. Not at the micron scale, not at the millimeter scale, they start changing at the nanometer scale. And this is why nanoscience and nanotechnologies are so exciting for many people, because if you control matter at that size, then you can really adjust the properties between atomic-like properties and macroscopic-like properties. This is the basis of nanoscience and nanotechnology. Another important aspect of nanoscale properties is that it's just not the size which is important. The structure also is very important. If you have a particle with the same size but a different structure, in some cases you may have very different properties. And we will see that especially in the case of nanotubes. All right. Another aspect to tell you how important those structures are is applied. Okay, we saw there was many patents already. So concerning the applied interest, the question I would ask is, does those material bring novel or improved performances? We don't care about knowledge. Industrial companies don't care about knowledge. They care about improved performances for improved profits, right? Okay, so performances. So what do we know about those new materials? What the new performances include notably the fact that they are very strong mechanically, because those structures are made only of carbon atoms. They are very homogeneous, and the C-C bond is also extremely strong. So it makes that you do not have any weak point in those structures. All the stress is all along the structure, okay? It is so you got an average stress, but no weak points anywhere. So this makes those materials very interesting in terms of mechanical properties. And in addition, carbon is a very light element, so it makes that you not only have something which is strong mechanically, but also something which is really light. So this is really interesting for many applications, like in aerospace, like in car manufacturing companies. Okay. Second thing is there is an excellent thermal conductivity of graphite along the plane. One plane of graphite, we will see later that a plane of graphite is called graphene, has a very good thermal conductivity along the plane. And this, for instance, gives you this value. This is quite a high value. It's much higher, for instance, than pure diamond, which is some material which is often used as a thermal conductor. So here we got something which has a very high thermal conductivity. In some cases, those materials can also be good electrical conductor. And they have two important properties. They have a high mobility. It means that charges like electrons and holes can move very fast. And the other thing is they can carry a lot of electrons together, a lot of current before breaking. Okay, you can put a lot of current in those materials before they break. So this is called the maximum current density, and it is one of the highest in the known materials. Okay, another important property is transparency. Those materials are not very transparent if you take them in bulk. Those among you who know nanotubes or graphite, they know it's just black. It's not very transparent. But if you take only one plane of graphene like this, it absorbs only 4% of light. It means that 96% of light goes through. So it's nearly transparent. And at the same time, it is very conductive. So it means you got a conducting transparent material. And this is very interesting for many applications. Would you have a suggestion for an application that needs a transparent and conducting material? This is a question. Do you know about ITO? Do you know about ITO? ITO is indium tin oxide, and it's extremely important for all flat screens. Most flat screens need an electrode on the top to conduct electrons and to address a given pixel. Okay? But if you got something which is not transparent, well, you cannot see anything. So for having a good material used as an electrode for the top of the screen, you need something which is conducting, of course, but which is also very transparent. And ITO is one of the only known materials which is both conducting and transparent. The problem is that indium is quite rare. There is less and less indium on Earth, and for this reason, the price is getting very high. On the contrary, There's a lot of carbon on Earth. Okay, and flexibility. This is also interesting because nanotubes, graphene, you can bend them. They are flexible, and even when they are bent, they do not lose their good properties like electrical properties and thermal properties. So this is the mixture of those properties which makes them very interesting. Not only something which is conducting, not only something which is flexible, but both flexible and conducting, both transparent and conducting. Okay, this is a combination of those properties that make those materials very interesting for applications. All right? Okay, I will not go in details through the properties, which will be the subject of the second course, second part of this course, given next week by Eric Anglare. Okay. Now I want to set the objectives of this course. So, este curso no es para mí. Este curso es para usted. The objectives of the course are that you learn something interesting for you. So I wondered when I prepared this course, what would have been useful to learn when I was your age? I don't think that it's interesting that I go in details, very focused details of a researcher in this subject. You will have a lot of time if you want to have detail. Come on in. If you... C'est bon? Okay. So, you will have a lot of time if you're really interested in this subject, if you become a researcher involved in this subject, to go into the details. So what I would like to give you is something general that could be applied to other things also, not just to this specific subject. However, it's important to know about the different types of materials, and carbon nanostructures are an important class of materials. So the first objective, of course, is that you learn some knowledge about this important class of materials. Then I would like to give you some important concepts in nanoscience, useful if you do nano research later. And these concepts are useful for understand, for model, for predict processes, behaviors, properties. And then I will also tell you about some techniques that a nanoscience researcher knows about and uses in order to learn about those theories, models, concepts, to design experiments, to test the models, and to collect the data. Okay? So these are the objectives of this course, and I hope to reach some of them. All right. Also, if you want to interrupt me at any time, if you have questions, just ask. Okay, this is the plan. So the plan is first to make an introduction about those materials. We will talk about the different types of bonding in carbon materials. We will talk about the possibility to create curved structures made of carbon only, and this will be the introduction. Then we will go during this course to structure. We will talk about the different types of carbon nanostructures. We will talk about which techniques we can use to characterize the structures, to check that what I say is not just my ideas, but it is experimentally verified. Okay, which techniques? And this maybe later you can, if you know about those techniques, you can choose the appropriate technique for a given information. Then as there is nobody's perfect in the world and no materials neither, we will talk about defects. Defects are important also to consider because in many cases they will impact on the properties of the materials. So this will be for today, and tomorrow we will talk about the synthesis method of those materials, the different ones and especially the most important one. Okay. Okay, now I start. Are there any questions before we go in the core of the course? Todo es bien? Okay. So, we start from the basics. So, all of you know that carbon has 6 electrons. If you want to feel the different electronic levels of one atom of carbon, then you should feel the different electronic levels one by one, from the less energetic to the more energetic ones, and then you end up with this electronic configuration for carbon. What you see is there are 2 lone electrons here, and then you can imagine that those electrons can create covalent bonds with other atoms in order to get into a more stable state. Okay, this is the principle of covalent binding in chemistry. But if you consider that, you see that carbon should always have how many bonds? There are 2 lone electrons, so carbon can only make 2 covalent bonds. Is it the reality? No. How many bonds usually can carbon make? Okay, organic chemists will tell you that carbon atom has 4 legs. Okay, not 2, nor 3. However, in certain cases, there may be not 4 legs, but 3 legs, and sometimes 2 legs for carbon. How to understand that? Actually, you need to consider this electronic configuration. How is it possible? Is it possible actually because the 2s state and the 2p state have nearly the same energy. So one 2s electron can easily go into the 2p state. And then what you actually have is this electronic configuration. And then you do not have 2 lone electrons, but you got 4. You got 4 lone electrons. They can create covalent bonds. Okay, this is for one atom. When you start creating bonds between atoms and make a molecule, you know that these atomic levels start to mix together, start to hybridize, and you create molecular bonds, molecular orbitals, by hybridizing those different atomic states. In the case of carbon, if you mix S states and P states, you can have different results. For instance, if you mix completely these 4 electrons, you use all of them, no one is left on the side, then you can create these sp3 molecular orbitals, and you got 4 bonds, 4 binding levels, and you got the 4 legs, which are well known for carbon. This is sp3. In this, all the bonds occupy most of the space in all directions, although they are directed in certain directions, but it's 3D. You got 4 bonds. And then you can have only one 2s and one 2p mixed together, and then the other 2p electrons left aside. And then you can create sp bonding, and then the other p are on the sides. What is interesting here is that you got linear bonding. It's just a straight line with sp orbitals. And then you can have an intermediate thing. You use one 2s and 2 2p. You create sp2 molecular orbitals, and you got this configuration where you got 3 bonds, 3 sp2 bonds, all in a plane, with an angle of 120 degrees between them, and out of the plane you got just these these remaining p orbitals, like atomic orbitals. So these are the three types of bonding you can have in carbon. Example of molecules and materials where you have such bonding are acetylene. Acetylene is sp bonds. Graphite is only sp2 bonds. You got in graphite these plane of graphene, one plane, second plane, third plane, and in the plane all the atoms are linked by sp2 bonds. Okay, this is why they are in a plane. And because of the angle between the bonds, which is 120 degrees, it makes hexagonals network, and hexagons, and you got an hexagonal network. Okay, we also talk about honeycomb lattice, like for honey. Okay. Another example is diamond. Diamond is only sp3 bonding, purely sp3. In this case, you see that you do not make planes. What you have is like a three-dimensional crystal. Okay, so this is example of different materials you can make with pure carbon and different types of bonding. Of course, in some materials, what can be supposed, you could have some sp2 and some sp together, or some sp2 and some sp3 together, either separated in space or locally on a one carbon atom you have some bonding which is not really sp2, which is not really sp3, but is something in between. Okay, because nature is complex. Okay, it's not purely one or purely the other. It can be a mixing of those two types of bonding, and we will see some examples later of that. For the next, we will only or mainly talk about sp2 bonding. This type of bonding is at the basis of all the carbon nanostructures that have been discovered and that we will talk about from now. First, I'd like to start by a question for football players. An important question for football players and for us is, how many pentagons does it take to make a soccer ball? Come on. How many years have you been playing soccer without knowing the number of pentagons in the soccer ball? No ideas? Make a guess. Guess something. 20. Okay. Someone else. 20 is less. Less than 20. Less. No idea? 6. 16. Too much. 7. Too less. Okay. To answer this question, we got a mathematical. There is Mr. Euler that studied polyhedra. This is a kind of polyhedra where you only have hexagonal or pentagonal faces. Football players, you confirm only hexagon and pentagons in the soccer ball. Okay, only pentagons and hexagons, nothing else. So if you use this law for polyhedra, Euler says that the number of faces minus the number of edges plus the number of corners must be equal to 2. Faces or corners. Corners is that corner at the corner of a face. Then you got edges between two faces, and you got faces which can be hexagonal or pentagonal. Okay, so we can make a short calculation. The number of faces can be either pentagons or hexagons. So the number of faces is, I would say, h, the number of hexagons, plus p, the number of pentagons. So this is H plus P. All right? And then we got the number of edges. Edges are always shared between two faces. So it means that when you got this number of pentagons and heptagons, they will always be shared between two faces. So then you divide this number by 2. The number of corners. A corner is always shared. We are locked. The number of corners is always shared by 3 faces. Okay? So this is, here we will divide by 3. And this total number is equal to 2. And at the end, if we solve, we got P equal 12. In a polyhedra with only hexagons and pentagons, the number of pentagons will always be 12. Always. For something which is completely closed. Completely closed. And the number of hexagons, well, it can be any number. There is no plane. Okay? What do we learn from that? What pentagons are useful for? Soccer player will tell you pentagons are important to close the soccer ball. Without pentagons, you do not have a curved ball. So it's no use playing with something flat. It's much better with a ball. So you need pentagons. Pentagons bring the curvature to this flat hexagonal network. And we will see how important this is also for materials, making materials made of sp2 carbon. Some examples. The first example is fullerene, which was also called before footballen. And soccer players understand why. It looks exactly like a soccer ball. And in this molecule, which is only made of carbon, and which was discovered by researchers in 1985, you've got exactly 12 pentagons. You got one here, one in the back, and if you count all of them, there are exactly 12. 12 pentagons. Each pentagon brings a curvature, a positive curvature of pi over 3. Okay? This is a solid curvature. It means that when you close completely the space with a solid curvature, the total is 4 pi. Okay? It's not like in a plane. In a plane, all of you knows that it's 2 pi. But in space, it's 4 pi. Okay? The full curvature. Alright? So here, if we bring 12 times pi over 3 gives you 4 pi. So this structure is fully closed like a soccer ball. Now you could have one molecule like coranulin where there is only one pentagon. And then the curvature, the solid curvature, or which is also called the Gaussian curvature, will only be pi over 3. And it will be noted as positive. This is an example. Now I take another example. This molecule is called 7-circlin. Instead of a pentagon at the center, you've got a heptagon. And around it, you've got 7 hexagons. This is a kind of different curvature. Instead of having a Gaussian curvature, which is positive in both directions, in this case, you've got a declination which is positive in one direction and negative in the other direction. Like the seat of a horse. I don't know the word in English, okay? But this has the same shape. Those who understand may translate in Spanish for the other ones. Okay? Now, here, what we get when we have a heptagon is a negative curvature of minus pi over 3. So it's a different type of curvature. And if we combine heptagons and pentagons, we can adjust the curvature. If you got one pentagon and one heptagon in the structure, then overall it's flat. there is no curvature because the pentagon curvature is compensated by the heptagon curvature. All right? So this is an example, another example of a structure called a nanohorn, okay? And where there is 5 hexagon, 1, 2, 3, 4, 5. In this case, the curve, it's not completely closed. It's not like we have 12 pentagons. It's not like it's half closed. It's something a bit less than half closed. You still have a shape at the end which looks like a cone, which is conical. This is another example. And the curvature is 5 times pi over 3 because we've got 5 pentagons. Easy. Okay, this was an introduction to the effects of adding pentagons, heptagons, I mean any kind of non-hexagonal rings in an hexagonal network. We create curvature. Okay, now I will describe the different types of carbon nanostructures that you can create based on those concepts of sp2 bonding and mixed with some pentagons, heptagons, and maybe in some cases some sp3 character in addition to sp2. This I already presented is graphene. So this is the basis material of graphite. Graphite is made of several planes of graphene, differently stacked. And this is graphene. In graphene, you see that you've got only sp2 bonding, just flat bonding. So it makes a purely hexagonal network. You see, this is only hexagonal network, which is also sometimes named as honeycomb lattice. So this material was actually very recently isolated. It is known for a very long time that graphite is made of this type of planes. But in the past, it was never possible to isolate only one plane of carbon like that, which is graphene. Just very recently, some people in Manchester, those 2 guys, succeeded in isolating one single plane of graphene on a surface, and they start studying it, and they found that they had this material has very new and interesting properties. Today about structure only. If we look at the structure, this obviously looks like a crystal because we've got a translational symmetry. But the translational symmetry, which is the definition of a crystal, okay? In a crystal, you've got a translational symmetry. If this is a 3D crystal, you've got translational symmetry in 3 directions. Here, this is a bit different. It's a 2D crystal. It's just in a plane, okay? So we've got translational symmetries, right, but only in 2 directions. So there should be 2 lattice vectors. Those 2 vectors are called A1 and A2, and they are actually they have the same length, but they have an angle between them, which is here. Okay, then we've got vectors. Those 2 lattice vectors, they will define the unit cell of this 2D crystal. So the unit cell is indicated here, and we may find out how many atoms this unit cell has, and we see that there are only 2 atoms. Those 2 atoms are a bit different. You need 2 atoms in the unit cell to create a graphene lattice. Okay. So keep this in mind. It's very important to remember these 2 lattice vectors, A1 and A2, to define the plane of graphene. We will use later for other materials. Now, if we start from graphene, we can do many things. For instance, I already presented graphite. So if I take several planes of graphene, and if I stack them together in some particular stacking configuration, I will make graphite. As you see, graphite is a three-dimensional crystal. Now, I may take only one plane of graphene and roll it. If I roll this plane of graphene and close it, I can make a tube, a tubular shape. These are the families of carbon nanotubes, and this time this is only a tube, a cylinder, so it's a one-dimensional structure. And if we repeat this unit several times, if we create a translational symmetry in only one direction, then we will create a one-dimensional crystal. Okay? Because there is translational symmetry in one direction. Now, if I take a few hexagonal rings, well chosen, and if I start to close them, I can make this type of closed structure, which is called that we have already presented before. Of course, when closing these hexagonal rings, we've been careful creating what? Say pentagons, right? We need to create pentagons. Pentagons were not present before. So when we closed, we created many pentagons. Actually, we created 12 pentagons to create the appropriate curvature to fully close the polyhedra. Here, there is no translational symmetry. So this object is just called a 0D object. Well, there is some symmetry, but not translational. You've got many symmetry, axial symmetries, actually. If you rotate it, there are many symmetry axes in this molecule. It is a very beautiful and symmetric molecule, but it's not a crystal because there is no translational symmetry. Okay, so now we got these different objects. We've got graphene, we've got carbon nanotubes, we've got fullerenes, and these three types of materials are what are called carbon nanostructures. So we have already presented graphene, and now we are going to go to carbon nanotubes and fullerenes. So nanotubes, as I said, is obtained by rolling a plane of graphene on itself, and you can obtain this cylindrical structure. This is not the way nanotubes are actually made, okay? This is just to understand the structure. It's a conceptual point of view, all right? Nanotubes are not made that way. It's just to understand the structure. So conceptually, a nanotube can be explained by rolling a plane of graphene into a cylindrical structure like that. So at the end, this structure, this cylinder, will have a particular diameter. The diameter depends on the size of the graphene sheet I took to make the tube. All right? What is also important to characterize this structure? Would you have an idea? Especially those who do not work on nanotubes already. Say again? Conductivity. Okay, conductivity. I may precise my question. My question is, what other parameter, more than diameter, do we need to fully characterize the structure, the geometrical structure of this object? We got the diameter. Is there something else? The chiral angle. This guy works on nanotubes. Okay. What is the chiral angle? Okay. The other students cannot hear you, but I will repeat. what you said. So you see that here I choose to roll this graphene plane in a specific direction, the direction given by this vector. I may have chosen another direction to roll the sheet. I would have get also a tube. I would have to cut a bit the edges to them to stick properly one to the other, but I could have made a tube. Okay? So there are many ways to roll up this graphene sheet, and the angle I choose for this CH vector is called the chiral vector. Another way to understand what is chiral angle is to consider the angle between CC bonds in the tube and the axis of the tube. The CC bonds and the axis of the tube, there is some angle between them, and I can modulate it between 0 degree and 30 degrees. So what is important to consider to characterize this specific tube, this special tube here, is its diameter, okay, and also its chiral angle, which is the angle between CC bond and the axis. This is a way to describe the structure. With that, I know everything. I don't need anything else to describe this object. It's enough. So it's the first way. This is the way I've described here. Two ways to describe the structure of a nanotube. We can use the diameter and the chiral angle, and with those two parameters, I know everything. Now, it's a bit difficult to use, and some people thought maybe we could use this vector here, which is very well defined, because actually it is a sum of lattice vectors of the graphene. So here we got the coordinates of these vectors, which are two integral numbers, which define completely this vector, which is called the chiral vector. The chiral vector, as you see, is a vector which makes the circumference of the tube here, at the end when the tube is rolled. And this vector at the beginning is completely well defined in the graphene sheet here. I can completely define this lattice vector in terms of A1 and A2 lattice vectors of graphene. It's n times A1 plus m times A2. This is the definition of CH. And then, instead of using diameter d and chiral angle theta, I may use these two parameters, those two indexes, n and m. And this idea was put through by Mr. Hamada. That's why n and m are called Hamada indices or Hamada indexes. Okay? So those two ways are equivalent. At the end, I will exactly know the structure of the tube. It's the same. And a consequence is that there are relations relating d with n and m and theta with n and m. And those two relations are demonstrate that it's completely equivalent nomenclatures to use nm or d theta. All right? Okay, so you can also find back on this figure the theta angle. You see that the theta angle is the angle between the chiral vector and the A1 vector. Okay, theta is defined here. Now we are going to see different types of nanotubes. Those are examples of different nanotubes which were obtained from different graphene sheets at the beginning. You can have a 5,5 nanotube, 6,6, 7,7. Here, 7,7, 5,5 are NM. Okay, they are the Hamada indexes. You see that if I add some A1 and A2 in the graphene sheet, well, I got tubes of much larger and larger diameters. Okay, so these are some examples of nanotubes you can obtain. The message here is that you can make very different nanotubes. There are a lot of different nanotubes. Actually, there is an infinity of carbon nanotubes that you can make. Okay? There is just not one nanotube or a few nanotubes, not just those, but there are many ones. Okay. Here is an example of the Hamada indexes that you could have, that you could use to make a nanotube. We already saw 5,5, 10, 10, and so on. So 5,5, for instance, is here. The 5,5 tube in this graphene sheet is here. It means that if I want to make a 5,5 nanotube, I will roll this graphene sheet in order that this point, 0, 0, covers this 5,5 point. Okay? By rolling it this way, I will get a 5,5 tube. And there are many other ways to roll, and I can get many tubes. So here I will just talk about vocabulary, a new vocabulary which is used to define, to describe the different tubes. There are 3 types of tubes which you can obtain. If you roll in this direction here, along this direction, you will get this kind of tube which is called armchair. If you roll in this direction, you will get tubes which are called zigzag. Why armchair and zigzag? If you look at the circumference, you see that carbon bonds look like armchair, and here armchair bonds make zigzag lines. Okay, this is the reason for these names. All right, zigzag tubes, armchair tubes. Another way to define them is to consider the chiral angle. The chiral angle for armchair tubes is always 30 degrees. The chiral angle for zigzag tubes is always 0 degrees. So it means the CC bond angle between the angle between the CC bond and the axis here is 0. Another way to define them is not to use the chiral angle theta, but to use the Hamada indexes. And you see that in this direction the Hamada indexes are always the same. N is always equal to M. So another way to define an armchair tube is to say N equals to M. This is also a definition of armchair tubes. All the tubes, all of them are armchair. 5 to 10, 10. What about the other tubes? Because there are many other tubes which have a chiral angle between 0 and 30. Actually, they are called chiral. Chiral angle because here in this case you have a mirror symmetry. You can have a mirror plane here and you got a symmetry. So this is a definition of something which is chiral. Not chiral, sorry, not chiral. In this case, you do not have this mirror symmetry. So these tubes are called chiral. So it means that it can be left-handed or right-handed. Okay, some those who knows about DNA and many biological molecules know that many biological molecules are even left-handed or right-handed, and this is really important for their properties. Nanotubes, chiral nanotubes can be right-handed or left-handed. It's not like in many biological molecules there is no selection, and at least actually there is no selection during the synthesis. They can be either one or the other. All right? Okay? Okay. Diameter. Here I've used the word still-walled because later we are going to see that there could be more than one wall. There may be many walls in one tube, but for now we just consider a single wall. A single wall tube usually have a diameter which is between 0.6 and 3 nanometers. Why those values? Actually, if you want to make a tube which has a diameter less than 0.6, then you got a lot of strain because remember that sp2 bonding does not like to be bent as pure if there is no pentagon or heptagon. It should be flat. And here, do you see any pentagons or heptagons? There is none. However, there is some curvature, but not a Gaussian curvature, a local curvature. But this curvature is quite low, and you can get that without pentagon or heptagons, you need to put some stress on those sp2 bonds. They do not really like that. So it means at some point you bend them too much. There is too much strain in the structure, it's not stable. This is why if you want to make too small diameter tubes, they will not be stable, and this explains minimum value for the diameter. What about the maximum value of 3 nanometers? Then in this case, since this plane is quite flexible, like graphene, if the diameter is too large, then the tube can collapse on itself. Okay, like collapse, yeah, like a tube which is smashed. Okay, so it will just collapse on itself and stick to the other side. All right, you understand that? Or if someone has a sheet of paper, I can just show, like, this is a good example of a collapsed nanotube. Okay, the two sides have collapsed on themselves. At the beginning, we've got the rolled tube, and then at the end, it collapsed. This happens when the diameter is too large. This is why usually there is no or very little amount of diameter which are more than 3 nanometers. Here I talk only about single wall nanotubes, where there is just a single layer of carbon making the wall. There are other types of nanotubes. Yes?
Exists some difference between the properties of the 5 for 10 for 10 or armchair zigzag properties of this carbon nanotube? I mean mechanical, thermal properties, I don't know.
Okay, good question. So the properties may be very different between those nanotubes. Not a lot in terms of mechanical properties, but it's very different in terms of electronic properties and also as a consequence in terms of optical properties. Here, for instance, you will have a complete explanation about that during the next course next week, but I may say a few words already about that. So depending on the way you roll the graphene sheet and you close the tube, you can either end to this red spot or to a white spot. What is the difference between the red spots and the white spots? It's the electronic properties which are different. So the red one corresponds to tubes which are metallic, which means very good electrical conductors, like copper. On the contrary, if you end up on a white point, you will have something which is semi-conducting, okay, like silicon. So it means that the electrical properties and the optical properties are completely different depending on the way you roll up the graphene sheet. So this is a question of the electronic wave. So you need to consider the electronic wave, and you need to close the electronic wave when you close the tube. So it's a bit too short here to fully explain the reason for that, but next week you will have the full explanation. But you may already know that, as I said before, not only the size is important for nano objects, but also the structure is very important. Okay, now I said we can have other types of nanotubes, not only single-walled, but we can have tubes which are called multi-walled. Multi-walled tubes were actually the first to be observed, to be demonstrated. And a multi-wall nanotube, as you see here, is just many single-wall nanotubes which are stacked together like a Russian doll. You got many tubes in between, and it makes this structure. What is interesting is that the distance between the tubes, between those walls, is similar to graphite, to the interlayer distance in graphite, as we have seen before. Here, okay? In graphite, there is a specific distance between two layers. Is there a specific distance? This distance is due to van der Waals bonding, due to the P bonds that we have already seen. You remember that when we make sp2, there was one remaining 2p, which was just left on the side, but it's still there, and it can create covalent bonds between the planes. Okay, so it's different type of bonding. It's not sp2 bonding in the plane, but it's van der Waals bonding out of the plane. And this bonding is much weaker. Van der Waals bonding is much weaker than covalent bonding, but it will set a specific given distance between two layers of graphene. This is the case of natural graphite. It's also the case in multi-wall nanotubes. It's because multi-wall nanotubes are just in some way bent graphite with many layers of graphene. Okay, this is bent graphite. As a consequence, the van der Waals distance is close to graphite. It's about 3.4 angstroms. In this case, the inner tube may be stabilized by the outer layers, and as a consequence, you can make smaller diameters because of this stabilization effect. So it means that instead of having a minimum diameter of about 0.6, there have been observations of inner diameter or inner tube of multi-wall nanotubes which were as small as 4 angstroms, 0.4 nanometers, because of the stabilization by the outer layers. The outer diameter can be very, very large because in this case, the outer tube cannot collapse thanks to the stabilization by the inner tubes. Okay, it prevents collapsing because these tubes are much more rigid. They are not flexible like single wall tube. And then the outer diameter can be very large. There is no theoretical limit. Experimentally, it can be as large as several tens of nanometers, or 100 nanometer, 150 nanometers can be very large. This is an important class of multi-wall nanotubes, especially for mechanical reinforcement in composites. In this case, usually as an average, those tubes are all metallic, as you will be explained in the next course. Okay, now it is important to consider the ends of the nanotubes. For now, I haven't spoken about the ends. It was just open ends. But in reality, they are not open. After being synthesized, usually the ends are closed. They are closed by these caps, these carbon caps you can see here, which all contain 6 pentagons. Why 6? Yes, it's half the space. 12 pentagons will completely close the space. Here, we don't want to fully close, we just want to close half the space and half the space on the other side. So here we just need 6 pentagons. So here, if you count well, there are 6 pentagons to give this solid curvature of 2 pi. Also, we saw that if we put some heptagons, we will change the curvature on the negative side. To compensate the existence of heptagons, we need more pentagons. And at the end, if we want a structure like that, which half closes the space, we need a number of pentagons that exceeds the number of heptagons by 6. Okay? Then we got this pi curvature. Here we presented a special case where there is, for this tube, there is only one possible cap for different thermodynamic reasons that I will explain. But for most cases, I mean for most nanotubes which have larger diameters, come on in. No, don't come. Usually there are many possible caps to close a given tube. You've got one possibility here, but there may be many other ones. For a given tube, many possible caps. But the other way is not true. For a given cap, you will make only one tube, because actually the structure of the tube will reproduce exactly the structure of the edge of the cap. So it's epitaxial reproduction of the edge of the cap. So for a given cap, only one tube will result. Okay? If you know the cap, the corresponding tube. If you know the tube, well, you don't know which caps could be at the end. There could be many different ones with different amount of pentagons and heptagons, such thing. Okay, now if I start reducing the number of hexagonal rings here and make the tube shorter and shorter and shorter, I may end up with something like that. Okay, it's exactly the same here, the same structure. I just removed some hexagonal rings here, and then I got this one. If I remove one more, I got this. If I remove one more ring of carbon atom, I got this. And this we already met. It's fullerenes. Fullerenes is just the general name of this type of structures, which are molecules composed entirely of carbon in the form of hollow sphere, ellipsoid, or tube. So for some people, usually the ones working on fullerenes, nanotubes are just a special case of fullerenes. But for most people, usually we use a different word for nanotubes. Because of their very long shape, we consider them to be a different class of materials. But considering the definition of fullerene, a nanotube could be considered as a very long fullerene. So we talked about fullerenes. Here are three types of fullerenes. Like nanotubes, there are many types of fullerenes, many different structures that are possible, on where you put the hexagons, on how many hexagons you add into. So you could have you have very different ones. They were discovered by Kroto, Curl, and Smalley in 1985, and they obtained for these results the Nobel Prize in Chemistry in 1996. Okay, as I said previously, with the soccer ball, there will always be 12 pentagons in those fullerenes, in those structures. Plus another rule. It was very rarely observed, fullerenes, where you've got two pentagons side by side. There is nearly none of them. Why is that? There was people who proposed that to have a stable fullerene, you should not have two pentagons side by side, because it's too energetic, it's not stable. And the name of this rule is the isolated pentagon rule, which was introduced by Harold Kroto. And this is something you also observe in nanotubes, those caps here. It's nearly impossible, very rare, to observe two pentagons side by side in the cap, like in fullerenes. So in addition to the rule of having always 12 pentagons, you also have the rule of having them quite far from each other. And this is the reason why it's very difficult to make fullerenes smaller than C60. There are some fullerenes smaller than C60, because C60 is the smallest fullerene where this rule is respected. If you go to smaller ones like C54, C56, you've got two pentagons side by side. No other choice. But those fullerenes are very unstable and very rare. Okay, here we got a lot of pentagons, a lot of local Gaussian curvature, and as a consequence, this is no more flat. So if we consider that this type of bonding, the curvature locally, is not only due to sp2 but sp3, we can explain this bonding of locally at the atom. It means here we've got something here, for instance, which is not flat. So one way to describe that is to introduce some proportion of sp3 in those. In this, you know, remember with sp3 you make like a tetrahedra with the 4 different bonds. Here it's a bit similar. It's like it's not purely sp2, but it's not purely flat, but you've got something which is a bit curved and looking like it's not sp3 neither, but it's a mixed between sp2 and sp3. For instance, C60 is considered to be something between sp2 and sp3, sp2.28, as experimentally measured. So you see that there is quite a lot of sp3 proportion in C60. And in C60 all the carbon are similar. So all are sp2.28. All those carbon have the same proportion of sp2 and sp3 locally. It means also that there is some tendency of these carbon to try to create sp3 bond out of the structure. Okay, so it explains why those structures have a much higher reactivity than something which is completely flat, because there is some tendency of sp3 bond to create, because it's already nearly created, this sp3 bond. So he explains that you can make a lot of covalent chemistry with fullerenes. It's an important area of research. On the contrary, if you want to create covalent bonds on graphene, it's much more difficult and you need much more reactive compounds. Okay, this was for fullerenes. So we saw the 3 types of carbon nanostructures: fullerenes, graphene, nanotubes. Now a question is much more fundamental. How is it possible to create those structures? I just say, well, carbon can make sp2 bonds. All right, you believe me. It can make pentagons, heptagons. It creates curvature. All right, you believed me. But how is it that those structures are stable? I don't know if I already showed any experimental pictures of those materials, but you believed me. I thank you for that. How is it possible? There is another reason. So, the question I want to ask you is, how is it that carbon, I just talked about carbon till now, not boron or nickel or cobalt, carbon, okay? Carbon can form those strange structures which are characterized by what? Those structures are characterized by a lot of surface. All atoms are surface atoms in those structures. None is inside the bulk, hidden behind other ones. They are all at the surface. And another interesting thing is they can be flat or they can be curved. So those structures are curved surfaces. How is it that carbon can do that? So the first part is curved. curved, it's all right. We have seen that. There are two reasons for that. You can make pentagons, heptagons, and for geometrical reason, when you put heptagon or pentagon, you create curvature. All right, you make some curved surfaces. And then you can also have some mixed sp2, sp3. It means the sp2 bond is quite flexible. It can bend a little and accept some sp3 character. It's not fully rigid. So you can create some curvature. But then what is strange with those structures is the amount of surfaces. You've got so much surfaces. It's quite unusual. Why is it that carbon is allowed to create structures with so much surface? Is it easy to create surface usually? Is it something which costs energy? No idea? The other people? No idea? No, they hide. Okay. So, create surface costs a lot of energy usually, and this is the surface free energy. When you want to split a crystal into and create surfaces, new surfaces, by splitting this crystal into, it costs energy. And the definition of energy is free energy, and the surface free energy is always positive, always, for any material. What does it mean? It means that it always costs energy to create a surface, always. Why is that? Because when you create surfaces by splitting a crystal, you break chemical bonds. You break bonds. And breaking bonds has a cost. And this cost, you find it in the surface free energy. This is why it's always positive. What is special with graphene and a hexagonal network of carbon? What is special is this surface free energy is very, very low. It's 50 millijoule per square meters. And for comparison, for nickel, for a crystal of nickel, the surface free energy on a given side, I don't remember which one, but on average, let's say, is 1,850 millijoule. Much, much more. This is why it's nearly impossible and it's very unstable, very energetically costly to create nickel surfaces. But creating graphene surfaces is much easier. Why is that? It's because all the bonds, when you got this sp2 bonding, are constrained in a plane already. So there is nearly no or very weak bonds out of the plane. So it's very easy to break those bonds. It's just van der Waals bonding. The cost, the energetic cost, is very low. This is why it's so easy to create surface of graphene and the derived materials like fullerenes and nanotubes. The value is very low, and the reason for that is because of this very special flat type of bonding, which is sp2. All right. So there are other types of materials that have a very low surface free energy. And those materials usually, like graphite, like to create layers that are stacked together in a three-dimensional material. They are not just graphite, which is a layered material with these stacked layers. There are many other ones, many other types of layered materials. Examples are BN, disulfide of tungsten, disulfide of molybdenum, and this kind of tellurium. They make layered materials. because they have a very low surface, and the consequence of that is that they have a very low surface energy, like graphite and graphene. And many people thought, well, we could make nanotubes and fullerenes with them, maybe. And they succeeded, actually. Example of a disulfide tungsten disulfide nanotube. You've got this hollow tube, and here you got a multi-layer of the tube. A carbon nanotube, but it's made of tungsten and sulfur. Okay. All right for that? And fullerenes also. I showed no pictures, but there are also fullerenes of those materials. They also exist. All right, so now I have finished with the different types of carbon nanostructures. And now you have to stop believing me about the structure of these materials. I am going to show you that it is real and how to know about the structure of this material, how to characterize it, and know about the crystal structure, the defects, and everything else which is real. So this is so in this part I will both make a short introduction on the different techniques that have been used and that could be used to characterize such structures, but it's not a course about characterization techniques. Okay, so I will be short. I may answer some of your questions on those techniques if I know them well enough, and then I will present the results of those techniques when used to characterize carbon nanostructures, and what kind of information you can get, and how useful those techniques may be for another type of studies. Okay, let's start by a very common technique, which is SEM, scanning electron microscopy. Many of you may know about it. Who knows? Who doesn't? Who knows about it? You all know, I guess? You're shy. Huh? Yes, you are. Okay, anyway, so a short introduction. So in SEM, you got this electron gun. You make an electron beam, accelerate the electron beam by an accelerating voltage. You focus the beam onto a surface. The beam will impact the surface. Then you use some other electrodes to deflect the beam in order to scan the surface. And then you have an electron detector, which is here for special types of electrons called secondary electrons, and measure the amount of secondary electrons emitted in each point impacted by the electron beam. Okay? And what is interesting is that you can then plot the intensity on a screen, and you get an image of the surface. So SEM gives you an image of the surface, which is the intensity of secondary emitted electrons. Okay, if we apply that to carbon nanostructures, and in this case to nanotubes, we see a sample of nanotubes. We see many filaments like that. We see that those filaments break into several others. They make like this Y connection, and you see that they are mixed together. So what can we learn from this technique? Well, we see the morphology, the microstructure, but we know nothing about the molecular structure. I mean, we know nothing about the diameter of the tubes, we know nothing about the chiral angle, and we know nothing, or let's say little, about the length of the tubes. We can maybe guess like a minimal length. That's it, nothing else. So SEM is good for morphology, microstructure, but you know nothing about crystal structure. Other technique is scanning tunneling microscopy. So this is a different type of microscopy. In this technique, we will use a conducting tip which will be put very close to the surface, and when it is close enough to the surface, we apply a difference of potential between the tip and the surface, we can create a current through this gap. The gap here is vacuum or air, so it's something which is insulating, but we can observe this current. This is a special type of electron current which is called tunnel, the tunneling current, through this insulating. And this current is only possible to measure if the gap, the distance, is very, very small, because it decreases exponentially with the distance. This is a characteristic of tunnel current. So we need to put the tip very close to the surface, but since this current is very, very sensitive to the distance between the tip and the surface, we've got to the distance between the tip and the surface. So if we keep scanning, can you hear? Yeah. If you keep scanning the surface with the tip and you measure the current as a function of the position, then you can have an idea of the topography of the surface. Okay, this is the principle of scanning tunneling microscopy. Okay, if we apply that to graphite, we got this image which shows very nicely the sp2 bonding, the honeycomb lattice of the top layer of graphite, and this is very, very similar to the case of graphene. We find those honeycomb lattices in both cases, so which confirms that it's actually sp2 bonding, and we got this very flat honeycomb lattice in both cases. If we apply that to the case of single-wall carbon nanotubes, we got this picture. We also find that we got this hexagonal lattice, like in graphene, but this time it is rolled, as you see here. Here is the tube, here is the substrate. The tube is here, and we see the hexagons of carbon, and you see that there is some chiral angle between the axis of the tube and the CC bonds, which is here theta. So this kind of characterization confirms that it's a hexagonal lattice and that there is a chiral angle. The chiral angle is not always 0 or 30. Okay? But this technique can also give you the diameter of the tube if you got a careful preparation. So this technique is very good for getting the crystal structure, to see the atomic details, but it requires very special conditions, like you need a surface which is very flat. If you use this sample, you will get nothing by STM. You need something which is already very flat. So you need a preparation, a flat sample. You need it to be very clean, of course, because if you got some contamination by air molecules, water, CO2, and anything else, then it will be very difficult to see these atomic details. So you need a very clean surface. And also, since we measure a current and we apply a difference of potential between the surface and the tip, we need both of them to be conducting. So the tip, it's okay, we choose it, but the substrate has to be conducting as well. So you need a conducting surface to apply this technique, STM. Okay, what else? TEM, transmission electron microscopy, which is also very useful for studying carbon nanostructures. So, the basics of TEM. It's very similar to SEM. At the beginning, you also create an electron beam. Here, you accelerate this electron beam, you focus it, but here, instead of scanning it over the sample, you will just make it broader in order to enlight, to illuminate a large surface of the sample. And then you will look through and look the electrons that have been transmitted through the sample. Of course, it requires samples which are very thin. If it's too thick, electrons will not go through. So you need a special preparation, and it's just possible for thin materials or materials that have been made thin by some special preparation techniques. It's okay, I do not speak too fast? No? Okay. Okay, examples. TEM was the original technique used to characterize nanotubes by Sumio Iijima in 1991, and these are the original pictures of Iijima, where he observed tubes of carbon with different amount of layers. Here, 2 layers of carbon, which is called double layer nanotube. Here, many other layers. I cannot see how many, but about 8, and here, like about 6. So with TEM, you can access a number of layers within a nanotube. You can easily distinguish them. It means that with TEM, in certain conditions, you have atomic resolution. You can see atoms. You can see atoms. You can resolve them. So this is called high resolution TEM. Also, tubes are often stacked, bundled together. And this explains this observation here by SEM. We saw these Y connections. Does it mean that one tube will split in 2 after some length? No, actually, what happens is that we have many tubes packed together here in something like a bundle, a wrap, and then at some point they split in smaller bundles, smaller wraps. And these wraps, they have some crystal structure. As you can observe here, you've got an hexagonal network. You've got a translational symmetry between this bundle of strings. So here, you understand that this is a cross-section of a bundle. Okay? Up to now, we saw the bundle like that from the side, and now we look at those tubes from the face, okay? Like cross-section. And we do observe that they are packed in hexagonal network, and what we observe too, what we confirm, is that they are tubes. The section is a circle. Up to now, we didn't know about that. It's just now that we realize that we've got tubes. Up to now, we saw that, but those may have been like a square section, a rectangular section. No, it's a tube. Okay? This technique also allows you to know about that. You can measure the diameter of each tube. Here they are very close to each other, for instance. Another example of characterization is with graphene. This is with an even better resolution TEM, and in this case, you can see atoms, and you can see the atomic plane of graphene, the hexagonal rings, and each black point is one carbon atom. And you also have some contrast related to the carbon-carbon bond, because you have some electrons. Actually, this technique is not sensitive to neutrons. It's very sensitive to the presence of electrons. So here, it's like a map of the electron density in this plane. Okay? TEM is very sensitive to the electron density locally. So this is why it makes like this hexagonal network. Okay, any question? Todo va bien? Bon. How much time is left? Okay, 20 minutes. Right? Okay, another technique, which is electron diffraction. I guess many of you knows about X-ray diffraction. You know about X-ray diffraction? Okay, X-ray diffraction is a very nice technique for material scientists to study what? The crystal structure, okay? You know the crystal structure using X-ray diffraction usually. Here, instead of using X-rays, we are going to use electrons. But electrons are also, you can also make diffraction with them, because as X-rays, they are wave particles. So there's an electronic wave associated with each electron, and these waves, they can interfere with each other and create a diffraction pattern, okay, which is required for the diffraction phenomena. So here we use electrons. There are two types of techniques. Either you use very high energy electrons, like let's say hundreds of thousands of electron volts, or you use low energy electrons, which are just a few tens of electron volts. You use this beam of electron and you focus it on the sample. Here the sample, you study the electrons which have been diffracted after the sample. So you study transmitted diffracting electrons. Here, on the contrary, with low energy, you will look at the electrons which are backscattered from the surface. Okay? In one case, you look through the sample, and the other case, you look at what is backscattered. But at the end, it's the same. In electron diffraction, what you get is an idea, a representation of the reciprocal lattice. Okay, so I will not go into detail, but you've got the real lattice of the crystal lattice, and the reciprocal lattice is a very convenient mathematical representation of this true real lattice in another space, which is called the reciprocal space, but which is just a conversion by a Fourier transform of the real space. So it also gives you the same information about the crystal structure of the crystal. Okay, so you got these sections of the reciprocal lattice, which looks like that. Here we are in the reciprocal space, and we observe dots, which correspond to a given family of crystal planes. Okay, like 100, 200. Those among you who knows a lot about X-ray diffraction will be familiar with this type of notations. The dots, the distance between the center of the picture and the dot gives you an idea, gives you a measurement of the distance corresponding to this family of planes. Like in X-ray diffraction, it's inversely proportional. Like in X-ray diffraction, the diffraction angle is inversely proportional. Okay, so we've got these measurements. This is for graphene. So if we make the Fourier transform of a graphene lattice, an hexagonal lattice, we also expect to get a reciprocal lattice which has an hexagonal symmetry. So here you observe very nice hexagons, and this is what we expect for a single layer of graphene. Now, if we study two layers of graphene stacked to get on one on another, we obtain this diffraction pattern. Is it really different? Actually, the symmetries are the same. We've got this hexagonal lattice, very similar, but something changes. What does change? Louder. No idea? The intensities, right? Okay, you observe that the intensities are not the same. For instance, in this pattern, those dots are the most intense, while this is not true in this pattern. What does it tell us? It tells us that the electrons diffracting by one layer and the other layer have interfered, and as a consequence of this interference, the intensities of a given dot has been modified. Okay, we could go to complex calculations to explain that in detail, but it tells you that electron diffraction allows you to differentiate between a single layer and two layers, even though they have exactly the same crystal structure. There are no additional dots here, okay? Because the two planes are just one and another and exactly similar. They are not tilted, they have exactly the same orientation. So as a consequence, the reciprocal lattice is the same. They just add up, one and the other. But there is this interference effect between the electrons diffracting by one layer and the other, and then it changes the intensities of each dot. But it does not create new dots. No new dots, just change the intensities because it's just the same plane without difference of orientation. They are oriented exactly the same, these two graphene planes. Okay? So, electron diffraction is really good, like X-ray diffraction, to determine the crystal structure, because in this case you will look to a lot of atoms and you will make an average of those symmetries to create this reciprocal space lattice. It's good also to know about the number of layers, as I showed you, and in the case where there would be a tilt angle between the two layers, you would be able to know. And I will show you an example later about that in the case of nanotubes, where you have this mismatch, this tilt between two layers, just after. Okay, this is the case here. A bit more complex, but if we have well understood about graphene electron diffraction, we can easily understand about the diffraction pattern of nanotubes. Okay, let's say this is second level course. What is a nanotube? Actually, in some way we could consider that a nanotube are just two layers of graphene stacked, one on the other, one on the top, on the bottom, one here and one at the bottom. This is some representation of a tube. In a first approximation, we do not take into account the tubular shape. Okay? As a consequence, what we would expect is just the same pattern as graphene, like this, the same pattern. And this is actually the case. We've got this hexagonal symmetry. We find it back in the electron diffraction pattern of nanotubes. We got this hexagonal symmetry. Here, this is the case of the zigzag nanotubes. It means that the top layer and the bottom layer have the same orientation. There is no mismatch, there is no tilt between the two. This is also the case for armchair nanotubes, except that the angle is different, but there is no misorientation, no difference of orientation between the top layer and the bottom layer. As a consequence, you've got just one hexagonal symmetry, but you see that this hexagon in this case is rotated by 30 degrees compared to this one because of the chiral angle which is different between the two tubes. Okay, hexagons pointing like that, In this case, hexagon pointing like that in this case. Now we take a more complex case, which is chiral. In this case, there is a difference of orientation between the top layer and the bottom layer. They are misoriented. As a consequence, what we get is the sum of the two patterns, orientation like that for the yellow one, and another hexagon oriented like that for the red one. One corresponds to the top layer and the other one corresponds to the bottom layer. What is nice with these hexagonal symmetries, which is also called six-fold symmetry patterns, we can measure what? What can we measure by the orientation of this hexagon? What does it tell us about? It tells us about the louder chiral angle. Okay? For these three examples, the only thing which is different is a chiral angle. Just that. So the chiral angle, you can measure it. It's just the orientation of this hexagon compared to this line I am going to talk about from now. But you can just easily measure this angle. In this case, you measure it twice. You got plus and minus this chiral angle, but these two hexagons are just symmetric compared to this plane. Alright? Okay. So with the orientation of this hexagon, you can measure the chiral angle. First thing. Now, what do we need to fully characterize the tube? We also need the diameter. Okay. So this is third level course. And what you will probably, or maybe you already know, or what you will learn in diffraction is the pattern given by a tubular structure. The pattern given by a tubular structure looks like this line here, which is called equatorial line in the case of nanotubes. And what you have is a dotted line with a special given frequency of this dotted line. So you get changes of intensities, but with always the same periodicity, the same period. And this period is simply inversely proportional to the diameter of the cylinder. So by measuring the distance between two maxima in this equatorial line, you can access to the diameter. Okay? So those are examples of the way you can completely know about the crystal structure of a nanotube using electron diffraction. Okay? Also, if I put more nanotubes, not just one, but a second one, then what will happen is the two diffraction pattern will add up. I will create a new one. So it will get very complex, but I can know about each tube. I can know about the diameter of each tube and the chiral angle of each tube. They will just add up. So I can also know about the number of layers. I can know about the crystal structure using electron diffraction. All right, defects. I'm at defects only. Okay. So I will go a bit fast on defects. So those materials, as any materials, are not perfect. And it can be observed, for instance, in this TEM image, that in this nanotube, this multi-wall nanotube, there are some kinks like that, kinks going upward or kink going downward. How do we explain those kinks? Those kinks here, like an elbow. These kinks are very localized. It's not like smooth change of curvature. It's very localized change of curvature. What happened there? What happened there is what is described here, is the presence here of an heptagon and the presence here of a pentagon. And this created this very localized curvature. At least this is the interpretation of the people who observed that at first they proposed that here are pentagons and here are heptagons and here are pentagons. How can we be sure about that? We can do other type of techniques, like the techniques I already presented. So among those techniques, which ones, according to you, can be used to study defects? One is easy, because it's already written. TEM. TEM, we got an image. So with TEM, we got an image of the sample, and if one atom is missing here, well, or if there is something added or something which is not symmetric, we can see. Okay, what about electron diffraction? Can we know about defects? Not too much. Especially if there is a low amount of defects, they will just be like average on this diffraction pattern. If we got something very disordered, very amorphous, then it will completely modify the diffraction pattern. All right. But here we're talking about just small amount of defects, localized ones. So diffraction is not adapted to do that. TEM is fine, and the other technique which is fine as well is, remember, other people? Other technique? No way. Yeah? No? Louder? STM. Scanning, tunneling microscopy. Why? Because we already also get this nice image, and this is just something, an area without defect. But there may be area with defects, and those two techniques, among the techniques I presented, are the main two techniques to evidence local defects by imaging them. So here, so it's not easy to see, but actually it's not only hexagons, but you also got those two rings here which are pentagons, and those two rings here which are heptagons. At the end, you've got two pentagons, two heptagons. What is the curvature? Come on, easy. $30? $15? It's 0. All right? Same amount of pentagons as the amount of heptagons. They annihilate each other, and it makes 0. The curvature is 0. You remain something which is overall flat. But locally, you've got some change of curvature. You've got this defect. Okay? What happened there, actually? To understand the creation of this defect, you may consider that this CC bond was rotated by 90 degrees from this figure to this one. And you see here you've got 4 hexagons, and by turning the CC bond, you transformed them into 2 heptagons and 2 pentagons. And this defect is called a Stone-Wales defect. It was predicted a long time ago, because it's quite easy to make it. The energy needed to turn this CC bond is not very high. You need to go from this state to this state, and you see that the activation energy to go from this very stable state to this defective state is not so high. This is just a calculation. It's several EVs, which is okay. Of course, the defect is less stable than the very crystalline structure, so you've got a difference of energy between the two states, which is called the formation energy. You need to put energy, you need to give energy to create a defect. This is what it means. Okay. So this is tone wave defect observed by high resolution TEM here. You've got other type of defects. Very obvious defect is one atom is missing. This is called, in crystal vocabulary, a vacancy. An atom is missing. So what happens if an atom is missing? So you remove one atom here. What happens from simulations and from characterization by TEM is that there will be some reconstruction locally because this is not stable enough. So instead of having these 3 rings missing one atom, the rings will rearrange, reconstruct, and will form this pentagon ring. This final state is more stable, and at the end, instead of just one atom missing here and 3 broken rings, then you've got the formation of this pentagonal ring and this big ring made of 9 atoms, 1 pentagon and 1 nonagon. This is one type of reconstructed single vacancy defect called 5-9. Another example of reconstruction following the creation of a vacancy is this one. Here we removed by the mind 2 carbon atoms in the middle. Here also 2 carbon atoms were removed. And what happened is a reconstruction. The atoms created new rings, like a pentagon ring here. Another way is to create 3 pentagon rings and those heptagonal rings, and also this kind of structure. All those predicted reconstruction have been experimentally observed, as you can see here. 2 pentagons, and this is 1, 2 octagon, this octagon, and those also. So what you must remember is, following the creation of a defect, the system will try to go to a lower energy state by reconstructing its bonds. Okay. Another thing is not just reconstruction, but also migration. Defects, like in any crystal, can migrate and move in the crystal if you have enough thermal energy, for instance. And this was observed experimentally. Here in blue are pentagons, in red are heptagons, and you see that as a function of time, the position of the heptagons and heptagons move. They do not stay at the same position. When you hit them, they start migrating. So you see this migration. At some point, this defect can meet. In some conditions, they can even anneal each other to create something which is more stable and more crystalline. And this is possible according to calculations because the migration energies in this graphene lattice, in this carbon lattice, is quite low. It's several EVs, a few EVs, so it means that it's actually possible for these defects to go over this activation barrier and to move, to diffuse, to migrate in the graphene lattice. So here this is in the case of a nanotube. Okay, I will not go into details, but there are many other possible defects, like in 3D crystals, like adatoms, like a substitutional impurity, like a non-carbon atom in the lattice, like line defects. And also an important type of defects is just the thing that the fact that there is an edge to the crystal. The edge, the fact that you have a finite border, is a defect because the crystal is supposed to be infinite in all directions. It is not. So it's also a type of defect. Just having edges. Okay, so I will make a summary of what I said quickly. You can read that. So carbon can make sp2 bonding. it makes something flat, but you also can put some sp3 to have it curved. You can have pentagons and heptagons added in the structure to create even higher local curvature, Gaussian curvature. The three types of carbon nanostructures we have been going through are graphene, purely sp2, flat, nanotubes, which is rolled graphene. You've got this one-dimensional symmetry, centroidal symmetry. Fullerenes, which are fully closed, which are not crystals, no translational symmetry. And of course, in all those materials, you can have defects, and those are important for the properties, depending on the amount of defects. The mechanical properties, the electronic properties will be very different. And you, as a materials scientist and scientific, you have to take that into account. Just to end the story, we have found fullerenes. We have found later nanotubes. We have found even later that graphene could be isolated and studied. Is it the end of the story? Well, we don't know, but there have been some people who proposed new structures that could be demonstrated, that could exist, that could maybe be synthesized someday. And what are they? Here, for instance, is purely sp bonding. Just sp. You remember sp is linear bonding. So does this chain of sp bonded carbon atoms can exist? We don't know yet. It's called polyene with a Y. And also you can mix different types of bonding like sp and sp2, and you can create this kind of material. Or you can mix sp and sp3 and you can create this type of material. Can they exist? Well, we don't know. Maybe you will find out. Thank you. Thank you. And most important, do you have questions?
Thank you. How we can do for obtain a carbon nanotube without defects? How can I control these defects?
You mean during synthesis? Or can you make a nanotube without defects? Okay. I don't know. I never been able to make one without defects. But you need to control the growth conditions. We're going to talk about that tomorrow. But generally speaking, if you want to make something which is very crystalline without defects, you should allow the atoms to go to the most stable position. What does prevent atoms from going to the most stable position? Usually it's kinetic effects. So it's the fact that atoms do not have enough energy and time to go to the most stable position. So if you want to get something without defects, which is the most crystalline as possible, you need to give atoms time and thermal energy. So thermal energy, you increase the temperature, and time, you provide atoms very slowly, one by one, not too fast. Okay? And this is just a general concept when you do crystal growth, because those materials are just a type of crystals, special crystals, but crystal growth concepts remain the same. Are there other questions?
How do you know about the toxicity of the nanocarbon tubes?
Okay, so this is an important issue, of course, especially because nanostructured objects are expected to have different chemical interaction, physical interaction. So this is an important issue on nanoscale objects. How can you know? Well, there are people working on this subject, so it's just impossible just from knowing the structure to determine the toxicity. You need devoted studies very specialized studies to determine if the material can be toxic, at which amount, because of course in terms of toxicology, it's not only the pure reactivity, toxicity of the material itself which is important. It's also the amount of material. Water, for instance, can be very toxic if you drink too much of water. Okay? So it's also a question of amount. Well, I don't know if I really answered your question correctly, but I'm not specialist of toxicity at all. It's just from chemistry and physics point of view, it's very difficult to know about the toxicity, and you need to do devoted studies in vitro or in vivo to determine the actual toxicity of such materials. What we as scientists in materials, chemistry and physics have to be careful about is to remain concerned about the possible toxicity of any new materials we make in our lab. Any other question? Yeah.
You talk about the diameter, but the length is important in carbon nanotube. How many is the maximum length or minimum length?
That's true. I did not speak too much about the length. The length is not important for the crystal structure. Okay, it's just that you've got more. You translate more the unit cell to make something longer. Okay, so there is no maximum or minimum limit theoretically to the length of a nanotube or of graphene. Experimentally, what do we observe? Very short nanotubes, well, you can make just the shortest nanotube as possible. They have been observed. The longest nanotube presently, as far as I know, is one tube which is like 20-25 centimeters. For graphene, it's a real problem to make large patches of graphene, because usually when you grow them, we'll see that tomorrow, when you grow them, you usually have something which is polycrystalline, okay, like patches of graphene with different orientations. And what you would like for having the best properties is just a single monolayer, a monocrystal of graphene. At the present point, usually the size of these patches of graphene at best are about let's say hundreds of microns. Okay, I think we should stop now. I thank you. I see you tomorrow.